Hello and welcome to MOS Live. For today's Ask a Scientist program, we are joined by three scientists who study how our brains make sense of the sounds around us, and also what that might mean for building artificial intelligence models of sound perception too. So they are here to tell us all about those topics and also to answer some questions from you. But first, let me introduce myself. My name is Meg. My pronouns are she and hers, and I am really excited to be your moderator for this program. If you are joining us on Zoom, please feel free to start entering your questions for our panelists at any time by clicking the Q&A button at the bottom of your screen. If you'd like captions, you can also access those by clicking the closed caption button at the bottom and selecting Show Subtitles. If you're joining us on YouTube or Facebook, we are very happy to have you tune in, but unfortunately, we won't be able to see your questions at this time. So let's get started. I'd like to invite our guest scientists to turn on their cameras and mics now and introduce themselves and maybe tell us a little bit about themselves. So hello and welcome to MOS Live.
Hi everyone. It's so nice to be here today. Thank you so much for inviting us to this session of Ask a Scientist. We're all really excited to tell you about our research and to answer your questions. So as a brief introduction, myself and my colleagues, Dana and Andrew, who are here with me today, we're all scientists who work in the Laboratory for Computational Audition at MIT. So audition is our sense of hearing, and all three of us study how people hear. We are particularly interested in how our sense of hearing is changed by the world that we live in and by our life experiences. So for example, I do some cross-cultural research where I travel to a remote region of the Amazon rainforest in South America to study hearing in people with really different lives from what we might experience here in the United States. So I'm really curious about whether our life experiences change how we hear certain sounds and how our life experiences can change whether we like certain sounds, such as music. So we found, for example, that preferences for music seem to be really determined by our culture and what kind of music we've heard. Now I'll hand it over to Dana, who also looks at how people hear music, but using a really different approach.
Yeah, so hi, my name is Dana. My pronouns are she, her, and I'm a PhD student at MIT. And like Melinda, I study how people hear. But I take a pretty different angle, and I study how the brain helps us understand different sounds like music, but also things like speech. So in my research, I use an MRI scanner, which is just a huge magnet that we can use basically like a camera to look at what different parts of the brain are involved when people are doing different things, like when they're hearing sounds, in my case. And I'm trying to figure out whether there are particular parts of the brain that respond when we hear certain kinds of sounds, like music, more than when we hear other kinds of sounds, and what it is about music that that part of the brain is specifically sort of interested in. And I think that's really cool because it tells us about how our brains are organized and how it helps us understand all of the sounds around us. So Andrew also studies hearing, but from a very different angle from both Melinda and me. So Andrew?
Thanks, Dana. So I'm Andrew. I'm a graduate student in McDermott Lab as well. And I study hearing from using computer models mostly. So what I do is I build computer programs that work pretty similarly to how humans do. And they use AI, sort of like a Siri or Amazon Alexa would or something like that. And what we can do is by controlling the environment that these computer programs learn in, we can sort of see where they match up with human behavior and where they deviate from that. And so by looking at that sort of stuff, we can really start to figure out what parts of the environment cause humans to behave the way they do by using computer programs. So that's what I work on.
Well, thank you all three of you for being here. This is really exciting to hear all of these very different aspects of hearing. So before we get to our questions from the audience, I have a few starter questions to get the ball rolling. We are talking about sounds and how we perceive them. And one sort of basic question I have is, do all humans hear the same way?
Yeah, that's such a good question because humans are different in so many ways. We look different to each other, we behave differently from each other. So it's really interesting to question whether we actually all hear the same way or whether that also differs across people. So I've been trying to look at this question through my research, and my research seems to suggest that actually there's really a lot shared about the way that people hear the world. But what's interesting is how we interpret what we hear can be different. So for example, in Western classical music and most of pop music that you would hear on the radio, there are some combinations of notes called intervals that to us sound really sweet or pleasant or what's called consonant. And there are others which can sound really harsh or unpleasant or dissonant. And it turns out that this distinction between what's called consonance and dissonance is actually not universal. So the sounds that are really pleasant to us might not be really pleasant to people elsewhere. Some people, like the indigenous group that I study in South America, don't have this preference for consonance over dissonance. But it seems like they can still hear the distinction. So even though they don't prefer one over the other, they can still hear that there are these two separate types of sounds. So what we actually hear seems to be really shared across people, but how we interpret what we hear can really differ across cultures.
Yeah, that's super interesting. um, that sounds a little surprising to me, like to think that that there's some component of that that's universal, but so much of it is culturally determined, perhaps. And I just wonder, what are there any other surprising things that you've learned about how the brain makes sense of sounds? What surprises you the most?
Yeah, so I think we would all have sort of different answers about that because there is sort of so many surprising things when you study something like perception. But I guess for me, it's pretty similar to what Melinda was saying about how we all sort of hear differently. And to me, the most surprising thing is how we interpret sounds differently because perception is actually really complicated. So you might assume because, we're just going around the world, seeing things and hearing things, that perception is pretty straightforward, that sound happens out there in the world, and then the sound waves travel through the air and into your ears, that information gets sent up to your brain, and then your brain just knows what happened to cause that sound. And that makes sense. We just sort of assume that what we perceive is how the world works, and maybe it's affected by our cultures, but it kind of basically would work the same for anyone who grows up in the same sort of culture. But actually, perception is way more complicated than that. And that's because, like Linda was saying, the information that your brain gets from your senses, it might be kind of the same for everybody, but it's often incomplete or imperfect. So there might be multiple sounds happening at the same time, or maybe the sound that you're hearing is ambiguous and you don't know exactly what it is. And so your brain has to take all of that sort of messy information that it gets from your ears or from your eyes, and then put it all together and sort of make its best guess for what actually is out there in the world. And this whole process can differ across different people or across different times, which is why things like illusions work. So you have probably seen different examples of optical illusions and vision, different like the vase with or the two faces, and like which one do you see, and different people might see different things. But there are also a lot of auditory illusions. And so this is basically just a way that some sort of sensory information, either visual or auditory information, tricks our brains and makes us perceive something that isn't there. So I thought I would talk about just one example of that actually one of the other scientists in our lab sort of discovered somewhat recently. And it makes your brain basically hear something that isn't there. So what you'll hear, I'm going to try to play this sound, is it'll be a bunch of sounds of people clapping, so like a round of applause. And then after like a second or two, you'll hear a pretty loud noise interrupt the applause. But if you listen carefully, you'll still be able to hear the applause sort of continuing while that noise is happening. So let me try playing this sound. Cool. So did you guys hear the clapping continue through that sort of loud noise burst? All right. So what I did not say is that that sound actually didn't exist. So when that loud noise came on, I turned off the sound of the applause. It wasn't actually happening. But you kept hearing it because your brain was tricked. It's assumed that the applause probably would keep going because in the real world, that tends to be how things work. Sounds continue and they can be interrupted by other sounds. But that is an illusion. So I can show you that that's the case by playing the same sound, but now I'm going to turn down the volume of the noise so that it wouldn't cover up the applause in the real world. And you'll hear that it sounds like the applause stops. All right. So did you hear it? It sounded like the applause stopped and it was just the quieter noise. So yeah, that's one example of how your brain is actually doing something really complicated and filling in all kinds of information that it's not getting from your ears and your other senses. And so we're still learning a lot about how the brain does this. We actually don't know very much about how this happens in the brain, but it's sort of continuously surprising to see that your brain is doing sort of so much more than you might otherwise expect.
That is surprising. Your example almost is like an object permanence thing, but for sound instead of vision. That's so neat. um, so interesting that we're doing so much work in the background that is sort of hidden or covered up, and all we think that's happening is something that's so easy. Wow. Well, I wonder also about this other aspect where we have computer models of we're trying to understand or trying to be able to teach computer models to be able to hear. But I wonder, like, what about the interplay between those two things? Studying the brain, studying computers, what can one sort of teach the other or vice versa?
Yeah, that's a great question. And kind of going off what Dana said, the brain is doing all these really complicated things in the background, but a lot of it is influenced by the environment, right? So, you know how sounds kind of behave in the world, and you know how the world sort of behaves in general, the world you grew up in. And so one thing we can use computer models for is kind of investigating how those aspects of the environment shape your behavior. And the reason we can do that is because very recently we've both built computer models that can do things at the level of humans. So, you have like Siri and Alexa and things like that that can take words or listen to things and figure out what's going on. And then the second thing is we can simulate basically alternative realities now. So we can basically simulate entire auditory scenes and worlds with different aspects of physics. And that's because we have such powerful computers now. And so what we can do is we can basically raise these computer programs in different worlds. So we can say, well, what if the world didn't have sounds that continued, like that nicely? What if there was only ever one sound at a time? Or, what if there weren't echoes in the world, or things like that? And what we can do by raising these different computer programs in that environment and then looking at how they behave is we can start to attach parts of human behavior where the computer program and the human behave similarly to specific parts of the environment. So if we, train a computer model up and it behaves the same way as humans, and then we remove one thing and then retrain it, and that one aspect of the behavior changes, we can say, well, that thing in humans is likely caused by this thing in the environment. So we can really start to learn about how the environment is shaping the way we hear things and the way we perceive things in general. So it sort of gives us a way to do causal manipulations and experimental science in a way we just haven't ever been able to do before. So it's pretty exciting.
Wow. Yeah, we don't haven't had the chance to live in a different world with different rules in an
Exactly.
experimental sense. So that's really neat. And trying to think about a world without echoes and what that would mean, how that would change just how we live and perceive things. So interesting. I do want to remind our viewers on Zoom, if you have any questions, to use that Q&A box at the bottom of your screen, and we'll answer as many as we can. In the meantime, though, I wonder if you could each just tell us a little bit about how you became interested in this field of study.
I can start, yeah. So I grew up playing music. I played viola for most of my life, and so I've always really been just interested in sound and how we hear. And I've always just thought that hearing is sort of the most incredible sense we have, where we can take this information from the world and it can make us feel really intense emotions and have some, incredible memories. You can get so much nostalgia from listening to music. And so then when I went to college, I started taking some classes in psychology and neuroscience and realized that a lot of my curiosity about music could be answered using sort of approaches from neuroscience and psychology. And so I started working in that field. I started working in a lab that looked at music perception, and I've been kind of hooked ever since.
Yeah, and I guess I'll say my background sort of as a kid is actually very similar to Melinda's. So I was also a musician. I played the piano when I was little, and then I played the flute. And I really liked music and sound. And I thought that, speech was really interesting because it's just a sound, but somehow we're able to use it to convey meaning from one person to another. So it was all just very mysterious. But I actually started college thinking that I would be either a professional flute player or a music therapist. So I was still very much interested in music. And pretty quickly, I sort of realized that there were a lot of things that we didn't know about how the brain understands music and other kinds of sounds. So I got more interested in sort of the research where we could ask those kinds of questions. And so I changed my major. And after several years, here I am still trying to answer those same questions, but as a scientist.
Neat. Thank you.
So my background's I came more from the level of just how the brain does anything. I remember being in high school and just being, shocked that our entire world was built by, these brains, basically us, and we fundamentally didn't understand how they worked. And I thought that was crazy. And so I was really interested in neuroscience when I went into college, just more molecular neuroscience. And during college, I found out about computer science, and I kind of realized, well, wait a minute, we kind of understand how these programs work, and they're starting to be able to do things humans can do. So maybe this is like a good combo of, and like a good approach to studying the brain. So that's sort of how I got interested in this sort of computational cognitive science. And then perception, more specifically in audio, I think is just a really interesting domain, because the problems are these really like high level complicated perception spaces that are really difficult inference problems. And audio specifically, I think, is a great proving ground for some of these algorithms, because it's real world and really difficult, but has slightly fewer specific problems that vision does. So it's like a really good place to start, I think, when you're trying to figure out how things work. And it kind of generalizes. So it's that sort of reductionist approach in science.
Oh, that's interesting to hear. Well, thank you, all of you, for sharing that. We do have some questions from our visitors that are coming in. So I want to start with Lydia, age 5, asks, how does sound travel? And I might add to that, what happens to it when it gets to our ears?
Yeah, that's a great question. So a sound is just something that happens out in the world that causes vibrations in the air around it. So if something like falls down, or if you clap, you make the air particles around your hands start to vibrate, and they start moving back and forth, and they travel like a wave, kind of like, a ocean wave, or like if you have a slinky and you kind of make the slinky move. And so these sound waves of pressure travel through the air, and we can't see them, but the pressure waves come, and they come in your ears, and they make your eardrum vibrate back and forth. So the little thing in your ear that you try not to hit with a Q-tip, it starts vibrating back and forth. And that sends a signal up to the brain that there's a sound happening, and your brain has to do this big, huge, complicated amount of work to take just the vibration of your eardrums and figure out what the sound is and where it's coming from and what to do about it. So sound is just pressure, and it's a really interesting how it travels, and also how our brains figure out what is going on. I don't know if anyone else has more sort of information about that.
Well, I'll add just to sort of emphasize what Dana's saying about how complicated hearing really is. So imagine that you're standing at the side of a lake, and you can only look at the tiny little area. Maybe you're standing in the lake even, and you can only look at the tiny little area around your feet. But someone asks you how many boats are on the lake, or how many fish are in the lake, or what else is going on the lake, but you can only see these tiny vibrations that are hitting your feet. That's kind of what your ear is doing. It's just taking some vibrations from the world, from this really complicated world out there, and then we take all those vibrations in, and we can do these amazing things like hear speech and music and all the other amazing sounds we hear.
Great answer, thank you. We have another question here, which sounds like a question for Melinda, maybe. How do you foresee globalization influencing the cultural components of sound? Do you foresee a world in which sound perception will one day become universal? What a good question.
Yeah, that is a great question. Yeah, I think as our world changes, and so there's increased globalization where more people have access to phones and the internet, and just sort of there's sort of more global, like say, music infrastructure, for example. So people are hearing more of the same music around the world. I think that will change how people hear, because our experiences will become a bit more uniform. So like Andrew has studied, the world that we experience actually really changes how we hear. So as the world that we experience becomes more uniform around the globe, I think people will sort of begin to hear and interpret sounds more similarly. Anyone have?
But I'll also say that we'll definitely start to hear more similarly as we all start to live sort of more similar lives. But because perception is this sort of messy process where your brain is trying to make sense of things, even if we all live the exact same life, and you would hear certain things differently than the person sitting next to you, just because your brain is basically, it's making an inference, it's making a guess about what you're hearing. And sometimes our brains are going to guess differently. So we'll hear more similarly, but it's always going to be just a little bit different between people.
Just, um, I have another question here, but Andrew, did you want to add anything?
No, I think
Okay.
they did a great job. I don't have anything else to add.
Just want to make sure. Actually, I have a question, sort of going back to the previous one, about what happens in your ear when a sound wave hits it. I've heard of this thing called a cochlear implant, which is a surgery that you can have if you have a severe hearing loss. And my understanding is that that really changes the whole process that sound is entering your brain. So I wonder, could you tell us, how is that possible, for one thing, and then what is happening when somebody gets a cochlear implant?
So I could talk maybe a little bit about how it works. And I don't know, Melinda, do you want to say about how it changes the sound that the person hears?
Sure.
Or yeah. So basically what happens in sort of normal hearing is the sound wave makes your eardrum vibrate. Your eardrum causes the little tiny bones in your middle ear to start to move back and forth. The hammer, anvil, and stirrup that you might have heard about in a science class, they move back and forth, and they are sort of connected to the cochlea, which is a little snail-shaped organ in your ear. So it's actually in your skull, not the outside part of your ear. And that has sort of a spiral of different cells that we call hair cells. And they are sitting in this liquid that starts to vibrate back and forth with the sound wave, and it causes waves in this liquid, and the hairs on the hair cells start to move back and forth, and this whole big complicated process happens that basically causes these cells to transform the waves, the sound waves, into electricity, which is sort of the language that the brain speaks in. So it converts the waves into electricity and then sends that information up to the brain. And in hearing loss, there's a lot of different kinds of hearing loss, but one of the most common is that the hair cells in your cochlea die. You hear sounds that are too loud maybe, and the hairs sort of break off and the cells stop working. So they can't turn the sound waves into electricity anymore. And so there are some ways that you can try to fix that. There are hearing aids, which are they kind of go on the ear, and they basically are just like microphones that make the sound louder. So for some people, if they still have some hair cells left, making the sound loud enough will help them be able to hear. But some people who have very bad hearing loss or who have different kinds of hearing loss, it might be the case that none of their hair cells work at all. And so these are the people who get cochlear implants, and that can help them hear by basically replacing these hair cells and kind of sending the electricity itself from the cochlear implant into like the cells that carry it up to the brain. I don't know. You want to take over?
Yeah, sure. So, I mean, that's a great description, Dana. And these are really incredible devices. Someone who's profoundly deaf and is unable to hear can sometimes get one of these devices, and if it's working really well, could have a phone conversation. So, you know, they could have a full conversation without actually like reading lips or seeing the other person. They can just talk on the phone. So it's a really incredible device that can help restore hearing. But it is imperfect, and the world does sound different to people with cochlear implants. So, like Dana mentioned, inside this organ in your skull, you have hair cells. In a person with normal hearing, you'll have about 30,000 to 40,000 of these hair cells, so a lot of them. But on a cochlear implant, you'll only have about 16 to 30, so many fewer like single electrodes that will give electricity into your cochlea and send sound signals into your brain. So you're going from this really massive system to a very kind of constrained input into your cochlea and your brain. And so it's, I guess, if we're thinking about it in like a visual analogy, it's just imagine that the image gets a lot blurred, more blurred. So you can still maybe make out what's going on in the world, and you can still use that kind of blurry image, but it's not going to be the same crispness that you'd get from having normal hearing. So they're incredible devices, but they do change the way you can hear.
And for example, they cause problems in hearing things like pitch. Yeah. So the sound sounds kind of a little bit blurrier, but you also can't really tell the pitch of the sound. So you might be able to hear, it sounds almost kind of like a really harsh whisper or something, where you can kind of tell what's happening. You can hear some of the speech sounds, but you might not be able to tell if someone's singing or if they're asking a question. So that's one of the things that people with cochlear implants might have difficulty with, even if they can understand what's being said.
I would just add to that the representation that's fed in, like Melinda pointed out, is extremely different. But what's interesting is that the brain learns to adapt to it. So this sort of speaks to the just the remarkable adaptability of the brain. It basically decides, well, this is what I have. And so it like remaps its entire auditory system to use this signal and work with it. And that's, that neuroplasticity is what we would call that, is remarkable, because it's, it's just learned to use a totally different thing that it was never evolved to do basically.
Yeah, that is really amazing. I wonder, and Andrew, maybe this is a question for you. Are there any other things that you can think of that are coming where artificial intelligence, for example, might be able to assist people with hearing loss? What's exciting to you in that direction?
Yeah, I mean, I think there's a lot of things that are sort of moving in that direction. I mean, one field that gets a lot of traction, at least in the AI community, or sorry, artificial intelligence community, is basically speech denoising. So taking noisy scenes where you are, like, let's say you're in a restaurant or something like that, and really effectively filtering all that out. So doing all the work for you. So so it's almost like someone's wearing a microphone and you can just hear them directly. And they're making a lot of progress with that. The newest results are pretty shocking. And so I would expect to start seeing that appear in hearing aids and things like that in the near future. And so, there's a lot of room for those sorts of things. And I think your cell phone will do a lot of the work. At the end of the day, your cell phone's going to be the thing that's doing all the AI processing. But I do think that over the next 10 years, we'll see a lot of those advancements kind of leave the lab and actually start to help people, which is going to be great to see.
That's really exciting too. I'm just not just on the topic of hearing loss in particular, but are there any other future developments in sort of this studying sound perception and understanding that really, gets you all excited?
Oh, that's a good question. I guess.
Oh, sorry, Dana, go ahead.
No, you go. I was gonna just talk about nothing. So go ahead.
I mean, I think we're actually at a really exciting moment in auditory neuroscience, just because the methods that we have to study, like the methods that Andrew uses, like artificial intelligence and computer science, and the method that Dana uses, where she's doing this incredible brain imaging, they've just gotten much, much better recently. And so I think we maybe don't even know the questions yet that we're going to be able to answer. So we're just at this really exciting point where the field is really able to expand quite rapidly. So I think there are probably a lot of the new findings on the horizon, and we don't even know what those could be yet. So it's an exciting point to be in.
Well, that actually reminds me that there are a lot of cool sort of technologies that are just starting to try to combine artificial intelligence and sort of the models that Andrew uses with brain activity. So if you can tell from somebody's brain activity sort of which person in the restaurant they're trying to listen to, or where they're paying attention to and trying to focus on, you can use that to help filter the sound sort of even better. So if you tell that they're trying to listen to this person but not that person, you filter out all of that person's sound so that the person can hear the person listening to better. And that's something they're learning how to do now. And there's also sort of exciting ways of using brain activity to help people who might not be able to talk. So maybe they've had a stroke or something that makes it so that they can't speak anymore. But if we can tell from their brain activity what they're sort of trying to say, or just basically read their intentions, sort of mind reading, and translate that into a machine that talks for them, then they can sort of be able to have a conversation again. And so these sort of brain computer interfaces are still in very early days, but that's hopefully one way that we'll be able to use what we understand about how the brain understands sound, and then use that with computers to help people.
Wow, that is really exciting. Sounds right out of science fiction, but I guess we're making a lot of progress in that. That's really neat. That does look like we're getting to the end. We had some really fantastic questions in there. I think we didn't get to quite all of them. I'm sorry about that. I do have one parting question for our guests before we say goodbye. So my last question is, do you have, if you could give young scientists or budding scientists one piece of advice, maybe they're interested in going into cognitive science even, what would you tell them?
Well, I'm a little biased, but I would say learn a lot of math, and I think computer science is a very, very effective tool. So I really believe that a lot of the major innovations in the future will at least be driven by the ability to code and understand the math that you're working with. They're just these amazing tools, and they've really advanced the field already, and I think they have a lot more to offer. So I think that's a great place to study, and that's one thing I definitely recommend. Definitely recommend learning more of. If I had to give myself advice.
It's a good point.
And I'm jumping off that, but I'd say even though it could seem daunting to try to learn how to program or how to learn the math behind this, I would say just don't be intimidated. I think I was really younger when I was really nervous when I was younger, that science would be too hard or that I didn't know enough to be a scientist. But I'm really glad I tried. Science is so much fun to do, and being able to really push the boundaries of what we know is incredibly rewarding. So I just say don't be intimidated, give it a shot.
I was going to say the exact same two things, which is math and computer programming are really important, and they are tools that you can use to ask sort of even more advanced questions and be able to answer them. And I was also going to say not to be intimidated, because coming from sort of my background, which was psychology and music, this was all sort of new and intimidating for me. But even if you don't think you're a math person, or if computer programming doesn't sound very exciting to you, I would try it, because you might surprise yourself. It sounds like both Melinda and I were surprised when we actually sort of tried these things. And then the other thing, which I think is just as important, and I'm sure Andrew and Melinda would agree, is to stay curious. So even if you don't think that you're especially interested in science, or you don't think you're especially interested in the brain, or whatever, to just sort of keep asking questions about the things that do interest you. So like, for example, I was interested in music, and I didn't even realize until I got to college that that was something that you could study as a scientist. So even if the things that you sort of like don't seem like science, you might someday find a way to be able to answer the questions that you have using science as a scientist. So stay interested in all the things that you're interested in.
Wow, what a great collection of advice from all of you. Thank you. I'm going to invite our guests now to say goodbye. Thank you so much.
Great. Thanks for having us.
Thank you.
Great. And we have a ton of great stuff going on over at the Museum of Science at MOS at Home. So follow us on social media, or check out our website at mos.org/MOS at Home. If you enjoyed this program, please consider supporting the Museum of Science by visiting us at engage.mos.org/welcome. Your support will help us provide science experiences online, and can help us ensure that this content can be accessed from home at no cost. So thank you again for joining us. Thanks to our wonderful guest scientists. We had a great time with you today, and we will see you next time.